Okay, let's start with this 16.3. Let's review a little bit what we did in this section. 16.3 basically doing line integrals again. But we have fundamental theorem of line integrals that says that if the vector field is conservative, maybe I write instead of using the word if vector field is conservative, then the line integral or curve integral of f dot dr is equal to the potential function at the end minus the potential function at the initial points, so RB minus RFRA. Okay, where the the gradient of f is equals to the vector field. Okay, now because it's like, let's say this is the curve here and this is at RT and this is RA. This is when t equals to A and this is when t equals to B. Okay, and if it is conservative means this integral depends on the value at the terminal point minus the value of the potential function at the initial point, and therefore it is independent of path. Independent of path, whatever path you use, as long as the path is smooth and differentiable, then we have that situation. Okay, now the things that we will learn here, we will review again here, is if the vector field is conservative, then how do we find the potential function? Okay, actually let's do more. How do we know that the vector field is conservative? The vector field is conservative in two dimension. If the, let's say the vector field f is given by pq, two-dimensional vector field, it is conservative if p sub y equals to q sub x. You know what? I don't want you to misunderstand that as multiplication. So dou p dou y equals to dou q dou x. Okay, and that is because of Clairaut's theorem. Okay, that is because of Clairaut's theorem. Okay, and then how do we find the potential function? Well, you will see that the gradient of f, so dou f dou x will be p, dou f dou y will be q. Okay, therefore the function in terms of xy will be the integral of p as a function of xy dx, and it has to also be the integral of q as a function of xy dy. Okay, this function, potential function f here, has to be consistent such that the partial respect to x, the partial respect to y give us the p and give us the q. Okay, now of course it's better for us to just see that in examples. Let's take a look on number 6. Determine whether or not this vector field in number 6 to be a conservative vector field, and if so, we need to find the potential function. So let's see. The force vector field xy is 3x squared minus 2y squared, 4xy plus 3. Okay, that's our P, this is our Q. Okay, so P sub Y will be negative 4Y, right? Q sub X equals to 4Y. No, they are not the same. P sub Y is not equals to Q sub X, so the vector field F is not conservative. Okay, so we cannot, in other words, the fundamental theorem of line integral does not apply. Okay, as for number 6, that's easy. Number 14, find the function f such that the vector field is equals to gradient of f. So it is then it means it is conservative, huh? Okay, let's do number 14 and show that it is conservative. So that's the vector field. Okay, so the p xy, that's the x component of the vector field, that's 1 plus xy e to the xy. Now the q, which is the y component of the vector field, is x squared e to the xy. They don't ask us to show that it is conservative here. In fact, they already implicitly say this vector field is conservative. Okay, but let's do it anyway. Suppose I want to show that this vector field is conservative, then I need to do dou p dou y, which will be respect to y, that will be x e to the xy plus 1 plus xy times e to the xy times x. Is it right? While dou q dou x, that will be 2x e to the xy plus x squared e to the xy times y. You know what? The first one, let's put them together first. This will be 2x e to the xy plus x squared y e to the xy, which is the same to what we have, huh? Note that, which we expect because the question asks us to find the potential function. Okay, so we see that dou p dou y equals to dou q dou x. Therefore, the vector field f is conservative. Okay, let me do it on the right hand side instead. So I'll move this later. Now I continue here. The question is, find a function such that find a potential function. Okay, then the potential function fxy must be integral of p xy respect to x, right? That's integral of, dang, I think it's a hard integration, huh? Don't you think so? 1 plus xy e to the xy dx. So this is, I think I need to do integration by parts somewhere. So let me just repeat this first. This is e to the xy plus xy e to the xy dx. Respect to, this will be 1 over y e to the xy plus, do integration by parts, that will be y0, 1 over y e to the xy, 1 over y squared e to the xy. Let me write it properly. so that will be x e to the xy minus 1 over y e to the xy, of course, plus function of y only. Now, dou f dou y should equals to q, right? Now, but let's see what is dou f dou y first. Dou x dou y will be, if I do derivative, that will be x over y. So derivative of this respect to y, e to the xy plus respect to y, that will be, hold on, I still have this though. I have this part here. When I integrate that, I will give me 1 over y e to the x. Okay, so this will be 2 times, huh? So 2 times. I didn't do it right at the beginning, so I need to basically clean it up. Okay, so this will be 2 over y e to the xy. Oh, minus another one, huh? So it's just 1 time. Am I right? No. My bad. I don't need that. This guy, the integral of this give me this. Like this give me this. Okay, so then when I put them together, see, I have like terms to cancel there. I have x e to the xy plus g of y. The derivative of that respect to y will be, the derivative of that respect to y will be x squared e to the xy plus g prime y. Now compare that with q, which is q is just x squared e to the xy. So from there, g prime y equals to 0. So gy is just a constant c. Okay. So from there, we get, so the function fxy, the potential function, therefore, is x e to the xy plus constant c. Now, going back then, the question is find the integral over curve or path c of f dot dr, where the r is cosine t, rt is cosine t to sine t. The t is from 0 to pi over 2. Okay, so this will be integral from 0 to pi over 2. Actually, I don't need to, huh? I already have that potential function. Okay, so actually, yeah, I don't need to. So this is basically equals to the potential function at pi over 2 minus the potential function at 0, right? Okay, this is f at pi over 2, that's 1, 0, no, that's 0, 1, 0, 2, I'm sorry, this is 0, 2. At pi over 2, that's 0, at pi over 2, that's 2, minus, at 0, this is 1, 0. Okay, now I plug that in, 0, 2. So that will be C plus, I'm sorry, C minus, I plug that in so that you see what I meant. Okay, so F02 will be 0 e to the 0 times 2 plus C minus, at 1, 0, there will be 1 times e, 1 times 0 plus C. Of course, then because it's definite integral, right, the C will cancel. Okay, so we will get 0 minus 1, which is negative 1. Okay. Number 18, let me give myself some space. What is the question for number 18? The same thing, huh? Show that, find the potential function. So, oh, but this is three-dimensional. Hold on. This is three-dimensional. Uh-oh, I think I need to develop something. We will see in the next section what happens if the function is three-dimensional. The vector field is three-dimensional, and show how to show that the vector field is conservative. But for now, suppose my vector field F is given by PQR, the scalar function PQR. Notice that in 2 dimensions, we did the cross partial derivative for the position and set them equal. So one of them that it has to satisfy is dou P dou Y has to be equals to dou Q dou X. Okay, and dou P dou Z should be equals to dou R dou X, and dou Q dou Z should equals to dou R dou Y. Again, that's the consequence of Clairaut's theorem. Good thing here, they don't ask us to show that it is conservative. We just need to find the potential function. So assuming that it is conservative. However, for now, we can say that if you want to show that it is conservative, if we have this, okay, if we have the whole thing there. If we need to show that it's conservative, again, you can hold it on. Next section, we will see how to show, I think next section or the section after that, we will see how to show a vector field in 3 dimensions is conservative using the curl that we will see in the next section. Okay, so suppose it's conservative, then our P is sine Y, right? So our function xyz will be the integral of that sine y dx. That will be x sine y plus a function, or call it g1 of yz, because we integrate respect to x, right? In other words, the derivative of this thing, if we do the derivative respect to x, the g1 will disappear. Okay, that's for P. How about the Q? The Q, that's x cosine y plus cosine z. Then the function, the potential function, will be the integral of that Q respect to y. That will give us x sine y plus y cosine c plus another function of xc. For the r, which is negative y sine z, the potential function from that point of view will be integral of negative y sine z dc. That will give us y cosine c plus g3 is a function of xy. Now, put these 3 things together. What can you say about your potential function? our potential function must be x sine y. Let's take a look. The x sine y coming from this guy, right? And this guy, if you think about this, right? Okay, plus y cosine z. Let me use this color. Y cosine c is yc, yc, yc. So what is our function of xc then? It must be the constant part, huh? Right? Plus constant. Okay. In fact, the constant is always there though. The constant is always there. Okay. From there you see that this guy will be basically just 0 plus constant. Okay. Anyway, that's the potential function. Therefore, how about the integral over curve C of f dot dr? Okay, this will be the potential function at r endpoints pi over 2 minus the potential function at initial point at 0. Right? That's f at pi over 2. Let me write it down. Rt equals to sine t to t from 0 to 2 pi. No, pi over 2, not 2 pi. So the x component, sine pi over 2 is 1. T, that's pi over 2. This is pi minus at 0. That will be 0, 0, 0. Oh, okay. Then what is f1 pi over 2 pi? 1 pi over 2. 1 sine pi over 2 plus pi over 2 cosine pi plus constant, which you will see it's not necessary. Okay. The potential function, you still need to put the c. Okay, but when you compute the definite integral, you don't need to put the c anymore because they will cancel. Okay, this will be 0 plus c. As you can see, this is 1 minus pi over 2. Okay, that's for number 18. Let's go on. Number 24. Find the work done by force field F moving the object from P to Q. Notice that when they say moving the object from P to Q, they don't really say if it is a straight line or another path, right? This is one sign that this function, this vector field is actually conservative. But we still need to confirm that though. Okay, so this vector field here, the P is e to the negative y, the Q is negative x e to the negative y. Now P sub y is negative e to the negative y. Q sub x is negative e to the negative y. P sub y equals to Q sub x. Therefore, the vector field is conservative. Now let function fxy be the potential function of that vector field f. Then fxy must be the integral of p dx and also integral of q dy, right? That's x e to the negative y plus a function of y. This is integral of q respect to y will be x e to the negative y plus another function of x. But we can see this basically from here we see that the potential function is just x e to the negative y plus constant. Don't forget that. Okay, then the line integral over curve f of f dot dr will be the potential function at terminal point, in this case is 2, 0, minus potential function at initial point 0, 1. Okay, this is 2e to the negative 0 minus 0e to the negative 1. But that's basically 2 minus 0, that's 2. Okay, now that's the benefit of conservative, because then it becomes independent of path. Okay, so we don't need to know what path they use, you just need to know the initial point and then the terminal point. Okay, now we are basically done with this section, but some other discussion worth mentioning. Number 31 to 34, determine whether or not the given set is open, connected, simply connected. Note, a set is open, in this case a region is open, if it does not contain the boundary. Okay, a more technical definition is as follows: a set is open if, the technical definition, if for every element in the set, let's call that set D. Then for every element in D, there is a disk, element X in D, a disk centered at X, vector X or coordinate X, fully contained in D. Now think about this. Suppose you have a set D not including the boundary. Okay, now this is an open set if you can pick a point, every point in this set D, you can find a circle fully contained in that. Now compare to a set that is not open. A set that is not open, if it contains, part of that contains the boundary. So let's say this part here contains the boundary. Now imagine if I pick a point in D, which happens to be the boundary, any circle, any disk containing that boundary will not be part of D, right? Let's say this is the region D here. Okay, you pick a point, happens to be on that boundary. Because it happens to be on that boundary, any disk containing that point must include the region that is not in D. Maybe I put another color. This part here, this is not in D. Okay. So basically you can say a set D or region D is open if it doesn't contain the boundary. Okay, that's the first one. Second, what is connected? A set D, region D is connected if there is a path between, there is a path C, curve C, fully contained in that D from any 2 points, between any 2 points in D. So for example, the following D is connected. Okay, because what? You can pick any point in that D, and you can have the path fully contained in D. Now this is connected. Now of course, two sets are not connected if you can find 2 points, both of them in D's, but whatever path you choose to come from one point to another one, you must have part of that path outside of D. Okay, now this is not connected. Okay, now the third one, what is simply connected? A set D is simply connected if it doesn't have a hole. That's the easy one. If it has no hole. A more technical definition says that a set D is simply connected if every closed path, however you create a closed path, every closed path encloses a region fully in D. Okay. So for example, this one here. So this region D here, however you draw the closed path, okay, a closed path in that region, okay, it will enclose a region, all of them in D. Now this is simply connected. The one not simply connected, for example, if you have a donut. Okay, now you can find a closed path. This closed path is fully in D. However, it encloses some region not in D. It encloses some region not in D. That's because you have a hole in there. Okay, now this is not simply connected. Now, with this review here, let's take a look on number 31. Number 31, you have x, y is from 0 to 3. So if we have that coordinate system, okay, the y is between 0, not including 0, and 3, not including 3. This is the region, not including the endpoint, the boundary. So clearly that this region is, first it is open, right? Why? Because any point you choose, however close it is to the boundary, okay, however it is close to the boundary, you can always find a circle, or a disk to be more precise, fully contained inside the region D. Okay, can you see that? Okay, that's why it's open, right? Second, is it connected? Yes, because any 2 points you choose in here, you can always draw a path fully contained in that region. So it is connected. Is it simply connected? However you draw the loop, as long as those 2 points, as long as the path fully contained in the region, then the region enclosed by that path must also fully contain in the region. Okay, so not only it is connected, it is also simply connected. Okay, number 32. You have xy, the coordinate xy, where absolute of x between 1 and 2. Oh, okay. So it is between 1 and 2. The absolute. Oops, what am I doing? What did I do? Sorry. I already have that. I want it. Okay, change the color then. Between 1, absolute of x between 1 and 2. This is 1 and 2. Oh, but it's absolute, so it is also between -1 and -2. So the region that we are talking about is this. It's clearly not connected, and therefore it won't be simply connected. Are they open? Is this region open? Yes, because any point you choose, as long as in the any point you choose in the yellow region, there must be a circle or disk fully contained in that yellow region. Okay, so this is open. How about connected? Oh no, it's not connected, because you can easily find 2 points whose path from one to another point not fully contained, in the region. Okay, so this is open, not connected, and therefore for sure it is not simply connected. Simply connected. You will see that for the region to be simply connected, it has to be first connected. Okay, as if we are talking about the set of all connected, region, simply connected is a subset of that. So if it is not connected, it won't be simply connected. Okay, as for number 32, let me jump to number 34. Number 34, that's the coordinate, that's basically the whole plane except that 2, 3. The whole plane except 2, 3. Number 34, that's the whole plane except 2, 3. 2, 3. So this is the point that we exclude. Okay, everything else is okay. Is it connected? Is it open? Yes, it's open. Okay, because any point you choose other than 2, 3, you can easily find a disk, create a disk fully contained in the yellow region. Okay, so yes, it is open. Is it connected? Yes, it is connected. Because you can easily find any 2 points, you can always find a path fully contained in the yellow region, right? But it is not simply connected. It is not simply connected. Why? We can find a loop, a closed path, okay, that encloses a region not fully in D. In this case, you can find a loop enclosing 2, 3, right? But that 2, 3 is not in the yellow region. Okay. Now, some big warning. This confuses me a lot when I first learned topology, which is the discussion about open, connected, simply connected thingy. Okay, the node. Okay, not open is not the same to say that it is closed. Okay, the idea of openness is not opposite of closed. Yes, a door, if not open, is closed. Okay, but the idea of openness and closedness in math are not opposite of each other. Okay, you may have a region that is open and closed at the same time. Actually, the whole R2, okay, the whole R is open and closed. Now, of course, then what the word closed mean, that's something we will discuss in advanced calculus. Okay, basically the region that contains all the limits. Basically, it contains all the boundaries. Okay, so can a region be open and closed at the same time? Yes, all real numbers, the whole real line, right? For any point you choose, you can have an interval fully contained in that. Okay, and it contains a boundary because it has no boundary. Because it has no boundary, and therefore you can say it contains the boundary, which is nothing. Okay, in fact, empty set is also open and closed at the same time. Okay, yeah. Empty set, because you can't even choose a point from the empty set to create the disk. Okay, I know this is kind of strange, but just big warning. I think I want to say it now that not open doesn't mean it's closed. Not closed doesn't mean it's open in math. That's the part that make me confused for a long time. Actually, I remember when I learned that part, me and my classmate were confused for around 2 weeks until the professor actually reminded us, no, not open doesn't mean it's closed. Not closed doesn't mean it's open. And then we try to argue, well, a door is like, if it's not open then it's closed. I said, no, it's not about door. The way we define openness and the way we define closeness are not related. So a set may be open and closed at the same time. A set may be not open and not closed at the same time. Kind of strange one. Well, anyway, just to remind you that kind of a strange thing, this number 31 to 34 here is actually not necessary for our discussion earlier, but it will be necessary for our future sections. Okay, that's for now.